Welcome to a lesson with Dr. Powell. Let's talk about odd and even symmetries of functions. Odd and even. Now, these refer not to exponents, not to powers, not to numbers, but rather they refer to different types of symmetries, which are simply called odd symmetries or even symmetries. What is an even symmetry? An even symmetry is one where if I have something like this, I'm going to get the exact same thing um, over here. Of course, this would be an even symmetry, and notice that it even works. This isn't even really a function right here. It gets 2 points for that same, or 3 even for the same x value. However, you can still say that it has an even symmetry. It's symmetric across the y-axis. So that's an even symmetry. An odd symmetry is one where where if we have something like this, and if we reflect, let's start with that graph. If we reflect across the y-axis, we're going to get not the same function. But if we reflect across the x-axis, we actually get to the same thing. In other words, reflecting across the y-axis is the same as reflecting across the x-axis. That's odd, and it is odd. It's called an odd symmetry. It doesn't matter which axis you decide to reflect across, you get the same result, which is dotted here. So you don't get back to the same function, but rather you get the same result. Okay, so that's an even symmetry, even versus an odd symmetry. Now let's take a look how we can determine if a function has an even symmetry or an odd symmetry simply from its formula. So let's suppose that we have a function that looks something like this. F of x is equal to, let's suppose we have something like x times the absolute value of x minus x, say, okay, or x cubed maybe. That's good. All right, so we have this function right here. Let's determine if it has even symmetry, odd symmetry, or neither. How would we do that? Well, let's just think about what it means. We just perform a reflection. First, I mean, we can perform a reflection across the y-axis formulaically to this. And if we notice that that result looks exactly like the function equation, or it has the same graph as the original function, when we reflect it, then we know it's even. Okay, well, that would be good for starters. But if we don't get that, then what we should do is we should reflect it the other way and see if they're equal. Then we notice it's odd. Now, how do we reflect formulaically? Let's think about what that is. From our information, from our practice with graph transformations, reflections are done by changing, first of all, what is input into the function. So if you want to do a reflection across for where the x coordinates change, so reflection across the y-axis, you would need to change all the x values to negative x, because you're multiplying by -1 to reflect over. So that would be what's done to the input, like the inner box here. So all the x's are replaced by -1 in order to reflect across the x-axis. So, or the y-axis, I'm sorry, reflect across this way, across the y-axis, means you replace x with -x. All right, so we can do that. And here we would have -x. So we have f of -x. And if we want, for graph transformation's sake, why don't we just label this as y? Because that's our new function here. It's the same. So y is equal to this, and we just replace our x's with -x, and that'll be the reflection. So I'm just going to have a y there. -x times the absolute value of -x minus -x cubed. All right, let's see what happens. Well, when you cube, it's repeated multiplication, and this is like -1 times x. And so you can collect all your -1s you're multiplying together, which there's 3 of them, so it's -1 cubed times x cubed minus, and here the absolute value ignores the negative, so you may as well just write that. Here, we can just put a negative off the side if we want, like that. All right, notice -1 cubed is simply just negative, and a negative negative is a positive. So we ended up getting this. All right. All right. So this is what this function looks like when we reflect across the y-axis. And I kind of simplified it a little bit just so we can get a better viewpoint of it, and it might come in handy in the next part. Let's look at what happens when we reflect across the x-axis. That means we replace y with -y, quite literally. But if we solve for y, it's like making everything negative. So basically, it's taking the original, but just making everything here negative. So -x times absolute value of x plus x cubed. Notice these are the same. Hey, that's odd. Yes, so this function is odd. It has an odd symmetry. All right, let's just look at one more quickly. What about if we have f of x is equal to x divided by x plus x times the absolute value of x. Is this even or odd, or neither? Well, let's do the same thing. Let's reflect across the y-axis by replacing x with -x. And notice with here, the absolute value doesn't affect it. So we can just, may as well write that. Notice that if we factor a negative out of the top and a negative out of the bottom, we end up getting the exact same thing as we started with, which means the y value of this graph is the same as the y value of that graph, where we've reflected and we haven't reflected, which means that it's the same graph. We actually get the exact same graph by the reflection, which means it has an even symmetry, so it's even. Thanks for watching.